In this video, we're going to talk about the second derivative test that can be applied to critical numbers. So pause the video and try and calculate the critical numbers for this function and take a look at the concavity at each of those values. Now that you had a chance to solve for critical numbers yourself, we'll remind ourselves that the critical numbers are all of those points where the first derivative is either equal to 0 or undefined. So our first derivative is negative 15x to the fourth plus 15x squared. And while this function will never be undefined, we can calculate when it will equal 0. We'll divide both sides by negative 15, giving us x to the fourth minus x squared equals 0. And factoring out an x squared will tell us our x coordinates. X squared equals 0 when x is equal to 0. And x squared minus 1 is equal to 0 when x is equal to positive or negative 1. So I'm going to create a number line over here and just throw our values on there. X equals negative 1, 0, and 1. And this is just going to be a way for me to organize my work. Now the second part of the question asks us to determine the concavity at each point. Well, that's based on the second derivative. Let's calculate that. The second derivative of our function is negative 60x cubed plus 30x. And so determining concavity at negative 1, we'll plug negative 1 into our second derivative, and we'll get 60 minus 30, which is equal to 30. We don't really care much about the value. What we care about is the fact that the second derivative when x is negative 1 is greater than 0. That means that it is concave up. And what I'd like you to recognize here is, since we know at x equals negative 1 that there is a slope of 0, and we know that we have a shape that is concave up, we have just determined definitively that negative 1 is a minimum value for our graph. Let's try it with 0. Second derivative when x is 0 is equal to 0 plus 0. So that tells us that our second derivative is equal to 0. And now we're used to sometimes this meaning that there are inflection points, but since we don't know the concavity, or we have a concavity of 0 here, we're not sure whether that point's a min or a max. So this is kind of inconclusive about what type of value we have here. So we're going to come back to this and see if there's something that we could do next to solidify our understanding of the graph at that point. Second derivative when x is equal to 1 gives us negative 60 plus 30, which is negative. So f of 1 is less than 0, which means it is concave down. And concave down at a point where there is a slope of 0 tells us that this is a max value. So let's return to x equals 0 and see what else we might do to learn more at this point. Since we're used to the second derivative equaling 0 telling us inflection points, one thing that we might try and do is go and calculate those inflection points. We could see if there are any other values where the second derivative is equal to 0, and we could check concavity on either side of those values to see if we have any changes of concavity. But I'm more interested in figuring out whether or not x equals 0 is a min or a max. So I am going to instead return to the first derivative. And I'm going to look at what the slope is on either side of 0. So I'm just going to come up above our number line and do that. So I want to look at this interval and figure out what the slope is. And I'm going to look at this interval and look at the slope. And I'm going to see if the slope changes, if it goes from positive to negative or negative to positive. So let's throw in 1/2 into our first derivative. So f prime of 1/2. Here we have our first derivative here. Negative 15 times 1/2 to the fourth is 1/16 plus 15 times 1/4. These are basically the same thing, but 1/16 is going to make that smaller than 1/4 is. So this is going to be a positive number. So our slope here is greater than 0. I'll do the same thing for positive 1/2. Well, this should have been, that's what we just did. We just did positive 1/2. This should have been negative 1/2. So let's see if anything changes with negative 1/2. Well, negative 1/2 to the 4th power is still going to be 1/16. Negative 1/2 squared is still going to be 1/4. So we're actually going to get the exact same result for the slope for both of those values. So what it looks like is that on either side of 0, the graph is increasing. And so since the slope does not change, that means x equals 0 is neither a minimum point nor a maximum point. And you might wonder, well, how could that possibly be true? And I'll just give you a quick little sketch of what could be going on here. We could have a situation where at x equals 0, despite having a slope of 0, we see that there are positive slopes on either side, and it is neither a min nor a max. So what conclusions can we draw from this? Well, it is possible for us to apply the second derivative to critical numbers in order to determine whether or not there are values that are minimums or maximums. So we see that if c is a critical number and the second derivative is greater than 0, then that means the graph must be concave up. And the only way for that to be true, a slope of 0 and concave up, is if c is a minimum for the graph. Conversely, if c is a critical number and the second derivative is less than 0, it must be concave down, and that tells us that c is a maximum value. And then we learn that if c is a critical number and the second derivative is 0, or we didn't see this in our problem, but we might see it other times, if the second derivative is undefined, this is inconclusive. And one thing that we might do is we might return to the first derivative to check the slopes on either side of our critical number to determine whether or not the slope changes, and use that to determine whether or not our critical number is a minimum or a maximum. A couple practice problems for you here, so why don't you go ahead and stop the video and see if you can work through these two problems on your own, and we're going to talk about them at the beginning of class on Monday.